Welcome everybody to CPI and XCamp's USACO Open Contest Workshop. So from now until 8 p.m., we'll be covering the bronze and silver solutions. So bronze will take about an hour, and then we might take a break before we start silver solutions from 7 to 8 p.m. For bronze, we have three instructors from CPI, and for silver, we have um, two instructors from XCamp and one instructor from CPI. And as always, after the presentation, you can feel free to unmute and ask any questions, and also type in chat any clarifications that you might need as you're explaining. And then after we do the presentations, we're talking a little bit about the trends of the US Open contest, and then just like advice on how to prepare for future contests. Okay, without further ado, I'll hand it off to Ryan Fu to cover bronze problem one.
All right, yeah. Let me share my screen and then I guess I can get started. Uh, can you all see my screen?
Yeah.
All right. So I'm assuming you guys have read the problem before, but if you haven't, just as a quick overview, you have essentially a string of both Booleans as well as logical operators, which are and or. And you're given Q queries, which tell you that you're allowed to set from left to right inside your string to either false or true, and you want the entire expression to be equal to false or true, and you're outputting if that's actually possible to do for each of the Q queries. So I guess as with any problem, it's a good idea to like start with the sample to like make observations and to try to like get a feel for the problem. And this is also for people that haven't exactly read the problem yet. So I guess as a first query, we have 1, 1. So we're allowed to change everything in uh, this place, and we want the entire thing to be equal to false. But this actually isn't possible because we process ands first and ors second, and there's already a true statement over here. So no matter what this stuff evaluates to, we'll just or it with the true, and no matter what, the expression will still be true. So as you can see, the first one it's not possible to make it false. For the second one, we can change 1, 3. Um, and we want it to be true. Again, kind of like because of this true, it'll always evaluate to true no matter what. We can do the same for, or the third query is pretty trivial, I guess. You can change the value of the entire string to false, and then you're done. This query, you want it to be true, and you can change 3, 3. But again, this true here guarantees that the entire string will evaluate to true. So that's also a yes. For the same reason, this is a no. Same reason as the first query. For this one, you want the entire thing to be false. And we can see that if we make this to false, then false and true, since we process ands first, that'll be false. And then false or false is false. So this is actually possible. And then for 5, 5, true, we can simply just keep it as true, and the entire thing will evaluate to true. So I guess one thing that we can observe from this is that since we always process ands first and ors after that, we can break our sequence into a series of first a bunch of ands. Um, so first like a couple runs of ands, and then some ors. So like the structure of the problem looks like this. And to give an example of this in the sample, it'll look um, like this. And this enables us to like kind of visualize the way that we'll process each query kind of efficiently. Now, of course, I guess if you're looking at the subtasks here, it's pretty obvious how to get an O of NQ solution. You can literally just try to change each thing to false or true and see like the output. You do that for each of the Q queries. You'll process the entire string. That's an O of NQ, and I guess the implementation of that can be like left as an exercise or something. But we want to do better than that, and we want to solve the whole problem. So we want to probably solve it in somewhere near O of n time. And I guess this structure of the problem kind of allows us to uh, make a lot of simplifications enough so that we're able to solve the problem. So I guess we kind of have two cases in this problem, right? So case one, and this is actually the slightly easier case, is we want the Boolean expression to evaluate to false. So in this case, if we if we want our thing to evaluate to false, and let's say like our query is from here to here, um, since an or means that since A or B, etc., if even if even one of these evaluates to true, the entire expression is going to be true. So what that implies is that everything to the left of it must be false, everything to the right of our query must be false, and then our query must also evaluate to being false. And our querying evaluating to false, or like the query range, this I guess, because this is our query, so we can essentially combine these into, since we'll have like something and something and then our query and the rest of the run of ands. Since we can just let our query and change it to false, that will enable this entire thing to be false, because when you have one false in a run of ands, that entire expression will be equivalent to false. So all we need to do to check for case one is everything to the left is false, everything to the right is false, and then you're done, because then you can just set then you're done, because after that you'll just set your query to false and you're done. So that's pretty simple so far. The second case, which is slightly more complex, is if you actually want your thing to evaluate to true. So in this case, again, we can have like our series of runs. Like so. And let's say like again, our query can be something from here to here. So I think like the first thing is that using the same logic as the previous one, if anything here is true, or if anything here is true, and we only need one true outside of our query range, I guess. If anything outside is true, like if there's at least one true outside, then it's possible, because the ORs will just make it so that the entire expression evaluates the true. But if that's not the case, then we have that, oops, then we have that all of these are equivalent to false. That's also false. And so the only way that we can output yes is if we somehow enable this range to be true as a whole, because then we can still OR everything together and it'll still be true. Now, obviously, it'd be better for a query to fill in as true, since otherwise, if it's false, it's guaranteed to be false. But here we still need to check that this range is all trues, and this range is all trues. So, because if those ranges are not all trues, then like if there's one false here, then when we AND everything together, it'll just be false, and then the entire expression will be false. So this is like the first case for outputting yes, and the second case is everything like inside the bounds, I guess, or I'll call these 2 points the bounds, but outside your query is true. So again, we need these to be true. So with that, I guess this is all pretty like high level, but I think it'll make a lot more sense in the implementation. Here's code that gets AC. So you'll notice that there's like a couple of arrays here. I guess I'll explain what they do. So the first thing you need to do in this problem, I guess, is it's important to be able to find like the bounds, like these guys and these guys, because that's the only way you're gonna check if like these are like false or true and all that stuff. And also, since when you're checking true, you also need to check for false and true in that range. So one way you can do that is to have like a left endpoint array and a right endpoint array. And the way that we'll initialize them, or the way that they'll be defined, is left of index is like if your index is here and the first OR is here, it's going to be the last index that's next to the OR. So that's going to be left. It's going to be here. And then right is defined the same way. It's going to be the first one before the last OR. So that'll enable us to find this in this position in O of one time, which we need to do. After that, we have an LF and an RF array. Those stand for like left false and right false. And what that kind of it is, and what we're kind of doing with that is that when we're checking if this is going to be true or not, we need to check if there's a false in here and if there's a false in here. So like I think you can do this with some like range query data structure, like prefix sums or something. But another nice way to pre-compute it is you can just check for every indice, you can just check the first false to the left of it and the first false to the right of it. In that way, if we get our left index here, if we know that our first false is like over here or something, then we know that there's no falses over here and we'll be fine. But if the first false to the left of it is in this range, then we know that we're not fine and we can't AND everything to be true. The same says, and the same goes for the right thing. So for the right index, if we just find the closest false to the right of it, then we can simply check if it's over here, then we're good. But if it's over here, then we're not good, since it'll be inside this range and everything can't evaluate to true. So that's kind of checking for this thing. Now, I think the only final thing we need to check is to check if this is true and this is true, or rather just to check if there's any trues within these. And again, you can do that with any like range query data structure you want, but you can also do some nice pre-computation here. The way you do that, oh sorry, yeah, I forgot to talk about how you initialize left false and right false. But the way you do that is similar to the way you initialize this guy. So the way you do that is as you're iterating, as you're going along your array, if you encounter a false, then your left false of it just becomes this. And if it's a true, then you know that the closest false to the left is equivalent to the closest false to the left of the previous one. Oops. So that's how we initialize left false and right false. For right false, we just go in the other direction. And that's also how we can find the closest OR. Finally, we need to kind of have a nice way to check if there's any like trues to the left or trues to the right. And the way we can do that is to kind of pre-compute. And this is like to the this is to the left, I think. This is to the right. The way you can do that is we can pre-compute how how many total expressions that and to true. That's what val is here. And if it's equal to true, then we can set like our value to 1, and then that'll let us know that there is some run of ands that evaluates to 1 in our prefix, and that'll tell us and that'll give us again a nice O of one way to see if to see if there is a true in here or not, which will enable us to check again for if the left is false and the right is false for the false case. And it also enables us to check if there's at least one true outside for the true case. We do that for the right as well. In the query section, we just went over that. But if it's false, but if the left or the right has a true, and if it's false, it's obviously no, and if it's true, it's obviously yes. If that's not the case, if it's false, we can output a yes, but if it's true, we have to check if the falses are kind of close enough to it so that they are far enough so that they fall outside the bounds. If that's not the case, then we can output no, but if that is the case, then we can output yes, and the solution does get AC. Yeah. So if anyone has any questions, I guess you guys can ask them now. Seeing none, I guess I'll hand it off to the next person, which is Max, and I guess I'll stay here for like another 5 minutes just in case anything pops up, and you can send it to me in the chat or something. Thanks.
Max, we can't hear you.
Can you hear me now?
Yeah.
All right, and just confirming you guys can see my screen.
I think you close your screen share.
Oh yeah, my bad. Uh, can you see now?
Yeah, looks good.
All right. So this is problem 2 of the bronze. Farmer Gunners and Callison, each of them like to take a daily walk along the fence enclosing his pasture. So n is less than 10 to the 5. And the fence has p posts, and there are up to 2 times 10 to the 5 posts, and p is even. And the location of each post is just a different 2D point on a map of Farmer John's farm. It's basically like just like the point system, coordinate system. And the x and y position of each post is less than 1,000. So each post is connected to two adjacent posts by fences that are either vertical or horizontal line segments. So the entire fence is just a polygon whose sides are parallel to the x or y axes. So the fence polygon is quote unquote well behaved in that fence segments are only potentially overlapped at their endpoints, and each polygon aligns with exactly two fence segment endpoints. So every two fence segments that meet an endpoint are also perpendicular. So then each of his cows that takes the walk along the fence has a preferred starting and ending position, and each point is somewhere along the fence. It could be at posts, but it could also not be at posts. And each cow walks along the fence for her walk, starting from her starting position and ending her ending position. And obviously, like the fence is like a polygon, so there are two ways around it. And cows are lazy, so they just like to take the shorter path. And your goal is just for each cow, tell them how short the shorter path is. So the solution for this is just, well, the bounds are small, so you can just kind of maintain the position of each fence. So the input is really convenient. The fence posts are given to us in a counterclockwise order, so we know how the fence is laid out, and the x and y positions are less than 1,000. So we can just straight up have a 2D array that stores like whether or not there's a fence at a given position. And we can actually do better than that, right? We can just store like the quote unquote position of each cell on the fence. Let's just arbitrarily say that like the first fence post that they give us in the input is at position 1, and then the cell that's counterclockwise from that, so the one that's like 1 left or 1 down, depending on how like the next post is position 2, and so on. So and then the one after that is cell 3, and all the way until like the n minus or the nth cell is like directly to the right or above the starting cell. So yeah, we can sort of like label every single position on our 2D array as which position in the fence is in, or whether it's just not in the fence at all. And it also allows us to just find the perimeter of the fence, because like the last quote unquote position is just how long the fence is. And what we do is for each query, we just find like the difference between the quote unquote positions of the two cells they give us, and that's just the length of one of the paths around the polygon, and obviously the other path around the polygon is just perimeter minus that root. So this is a fairly straightforward problem to code. I'll just hop over to the implementation right now. So at the beginning, we just read in our input and we store them in two arrays. And then we have our 2D array that stores whether or not there's a fence there and what position the fence it's in. And of course, we have our perimeter variable. And then here we're sort of just looping through all the fences and labeling the positions of the array. So it might be like a little unorthodox implementation here, but basically dx is sort of like the difference in x position between each of the fences. So if the fence is a horizontal fence, dx is either 1 or -1. And dy is the same for vertical fences. So if it's a vertical fence, dy is either 1 or -1. And again, if it's a horizontal fence, since y doesn't change, dy is 0. And if it's a vertical fence, since x doesn't change, x is 0. So yeah, we just initialize dx and dy. And they're positive if it's going right or up, and negative if it's going left or down. Yeah. And then here we just do a while loop to just keep going until the next post. Every time, just increment the perimeter and just set the position of our current cell and change our current x and y position. Yeah, it's pretty simple. And then for each query, we just take in the cells they give us, and we take the positions of the cells. We find the difference, and that's one root. And then the other root is just the perimeter minus the first root, and we just take the minimum of the two. Does anyone have any questions? You can just drop it in the chat or unmute yourself. All right, if not, I'll just end it and hand it to the next person, which I believe is Andrew.
Andrew isn't here, so I'll be doing the third problem. Give me a second. Does this work? Uh, Hello.
Yeah, looks good.
Okay, cool, thanks. So this is the statement for the third problem, where Farmer John starts with a permutation of length p, and what will happen is he'll generate a new sequence h, which is generated in the following way. So first, he'll compare the first and the last elements of p, and depending on whether or not, if the first element is larger, he'll write down the second element in the permutation and remove the first element. Alternatively, if the last element is greater, he'll write down the second to last element and remove the last element. And in the end, farmer reverse John will have written down n-1 integers, which are the hints in that order. And then now, given the array of hints, farmer John wants us to construct a permutation that's consistent with the hints given. And out of all the possible permutations, we want to construct the one that's lexicographically minimal. Meaning that, like, at the first location that they differ, at the first position where two permutations differ, the one with the smaller value will be lexicographically smaller than the other one. So this is the problem. And before we get started on solving the problem, before we get to the solution, there are a couple observations that we have to make about the hints that are given. Yeah. So the first element, the first observation is that the last element in the hint must be 1. This is because the number 1 can never be removed from P, as whether or not it's P1 or Pn, it'll never be the larger of the two. So since the number 1 will never be removed, on the second to last, or on the very last comparison, 1 will be left behind, and it will certainly be written down. The second observation is that the number 1 can occur twice, but not more. And the reason it can occur twice is that if there's an element both to the left and to the right of 1, both of them will be removed eventually, right? Since 1 is the last number that will be removed, they both get removed. And when the element on the left is removed, 1 will get written down. And when the element on the right is removed, 1 will also get written down. So the number 1 can occur twice. And it can also occur once. But no, the number 1 cannot occur more than twice. And the third observation is that no number other than 1 can occur more than once. And the reasoning for this is similar. It's because a number can be written down if there's an element on the left that will be removed, or if there's an element on the right that will be removed. But the number 1 will either be on the left or on the right. And if the number 1 is on the left, then the number to the left of our current number will never be removed, because 1 will never get removed and it'll never reach that eventually. So for instance, if you consider the example I have down here, if you consider the 4 here, right? 1 is to the left of it, and this 1 will never get removed. So no matter what happens, 4 will only get written down at most once, because when the 2 is removed, we'll write down 4. So yeah, but by similar logic, no number other than 1 can occur in H more than once. So the next observation is that if an element is missing from H, so like H consists of the numbers from 1 to n, right? And if an element is missing from H, it is either P of 1 or it is P of n. And the reason for that is that those two elements will never get written down, right? Because you can write down P of 2, you can write down the second element, you can write down the second to last element, and you can write down all the numbers in the middle, just eventually. But you'll never write down the two numbers that are on the endpoints themselves. So if an element is missing from H, it is either it is one of the two endpoints. So these observations, well, in particular the first 3 observations, also give the conditions for whether or not a solution exists. If no element occurs more than once, except 1, of course, 1 occurs exactly once or exactly twice, and the last element is 1, a solution exists. Otherwise, the solution does not exist. So then there are 2 cases to consider in our solution. The first case is when the number 1 occurs once at the last as the last element in H, and the second case is when the element 1 occurs twice. So if the number 1 only occurs once, that means there's only the only permutation elements are to the right of it, or there are only permutation elements to the left of it. Because this means that because if there are permutation elements on both sides of 1, that means that 1 would get written down twice, right? Because when the number to the left is removed and when the number to the right is removed, they'll both result in 1 getting written down. But since 1 only occurs once, we know that one of those two cases won't happen. So there's only elements to the left of it or only elements to the right of it. And then since we want our array to be lexicographically minimal, 1 must be the first element in P. And the reason for that is that if P of 1 is equal to 1, that is automatically lexicographically smaller than if P of 1 is equal to n, or P of n is equal to 1, and P of 1 is equal to something else, because 1 is the smallest number there is, at least the smallest one that we care about. So this means that the missing number in the array, the h has length n minus 1, so there's exactly one number missing in the range of 1 to n. That element must be the last element in P, because this is related to the fourth hint, right? We know what P of 1 is, so the missing element has to be P of n. And then, but this also means that, so if we consider simulating the process, right? We know that the last element is greater than 1 because everything's greater than 1. So we know that the first number written down has to be the second to last element in P. So we know that h of 1 must be the second to last element in P. We know that h of 2 must be the third to last element in P, and so on, until we write down all the numbers up until h of n minus 2. And then we can skip h of n minus 1 equals 1 since we know where the 1 is. And with this, we can generate the entire permutation. And then in the example I gave, we can find that the final permutation will end up being 1, 2, 5, 4, 3, which I did not write down. Yeah. So that's the case where the number 1 only occurs once. So then if 1 occurs twice, we know that there's 2 missing values. This is because there's a total of n minus, or yeah, there's a total of n minus 2 elements that are not, no, there's a total of n minus 3 elements that are not equal to 1. And then there's one of them that's 1, which leaves 2 elements that are missing. And then let's call them A and B, and we assume that A is less than B. If they weren't, we can just swap them. To make the array lexicographically minimized, we would want P of 1 as A and P of n as B, because A is less than B, and having P of 1 be A will be better than having P of 1 be B, right? So then now if we consider the process, of writing down elements, we'll compare P of 1 and P of n, since we know what both of them are, and depending on the answer, we can remove one of them and write down h of 1. So for instance, if P of 1 is greater than P of n, then we know that the first hint, h of 1, has to be the second element, P of 2. And we know that P of 1 was removed on the first step. And similarly, if P of 1 is smaller, then h1 is P of n minus 1, or the second class element, and P of n was removed. And with this process, we'll always know what the first and the last element are, and we can simulate the entire process And we can use this method to place all the elements in P. Since there are a total of n minus 1 minus 1 equals n over 2 in H, other than the last one. Wait, no, yeah. There are a total of n minus 2 unfilled elements in P. It's n minus 1 minus 1 because the last number being 1 isn't helpful. So that leaves n minus 2 elements that will fill in. There's a total of n minus 2 unfilled elements in P. So this algorithm will certainly fill in all the elements in P. So like one of the important overarching themes is that after the first 2 elements are fixed, the process to determine the rest is fixed. So the lexicographically minimum condition only really applies to the first 2, to the first element and the last element in the permutation. The total complexity is O of n per test case, which will pass under the constraints that are given. And there's a bit of implementation for this problem. It's possible to make some bugs. So there's sample code provided in the paste-in link. And yeah, that's all there is for problem 3. So if I remember correctly, I'm also going to do like a rough overview of the USACO contest or of this particular bronze contest. And I think the most important thing for this contest is that since this contest is 5 hours long, the problems did end up being harder, especially in problems 1 and 3, and even in problem 2. A lot more emphasis was placed on writing good long code, uh, like as opposed to some of the previous contests. Like for instance, problem 1 is very implementation heavy for a bronze problem, and problem 2 and problem 3 are both on like the above average end. And this is because, after all, you have 5 hours instead of 4. So the problems they picked are different. And I think and also like it's very important to make good observations for all these problems. For instance, analyzing the casework on when the expression can be evaluated to true in problem 1, or noticing all these useful observations on problem 3. Um, making good observations and making progress on the problems is also an important part of this contest as well. And I think if we were to generalize the entire USACO season, most of the problems throughout the season or most of the contests throughout the season have really followed the idea of one easy problem, one like moderately difficult problem, and one extremely difficult problem. And I think that USACO is getting less and less afraid of making bronze people write long code. Even though, of course, what long is relative, to speak. But yeah, I think that's something to keep in mind. And as for practice is concerned, especially for problems like problem 3 from this contest, I'd recommend just doing problems off code forces. There's a lot of there's a lot of problems that on code forces that are like relatively speaking ugly. They're not clean to solve. They're not necessarily enjoyable to solve. But I think USACO is also moving away from problems that are clean to solve and beautiful to solve. So you can prepare for that by practicing on judges like that. So I think that's all for the bronze session. Someone from CPI or Charlie Washer would like to add something else. Yeah, but that's it from me.